Hello everyone, we are group number 62 and we are going to talk about stream and block ciphers. First we talk about the different types of cryptographic algorithms present and what type of algorithms we choose based on our preferences. Then we go ahead and introduce block and stream ciphers, and then we talk about how they differ and compare in terms of their mode of operation, in terms of keys that are used. Then we go ahead and discuss some noticeable block and stream ciphers. After that, we see some commercial applications and which block and stream ciphers are actually in use today and which are rendered useless due to vulnerabilities found. Then we go ahead and see some actually hardware implementations of specific cases for block cipher and stream cipher. And in the end, we will see a case study where the block cipher AES and the stream cipher RC4 is implemented on a single computer, and we see the difference between various metrics such as memory throughput, etc., and how it differs for both the algorithms. So since there are many cryptographic algorithms present in the market, the keyless hash function or the symmetric algorithms such as block and stream cipher or the asymmetric algorithms such as RSA, which one to choose? So the preference concern while choosing a cryptographic algorithm is mainly security and performance. So we have to choose depending on what we want and what is our priority. So in terms of block and stream cipher, the asymmetric ciphers, the block cipher is basically breaks down the plain text M into successive blocks of fixed sizes, and then it encrypts with a single key K. But in comparison, the stream ciphers breaks down the data in bits and then encrypts each bit with a K stream K. The main difference here between both the ciphers is that block cipher is a stateless permutation algorithm, a memoryless algorithm, whereas the stream cipher has an internal memory and is a finite state machine. Block ciphers, as we all know, consists of SP network, the substitution permutation network, and kind of a keystone structure, whereas a stream ciphers use the bitwise sort function for the plain text with the key stream to get the cipher text. And since it's both are symmetric ciphers, the decryption function is really the inverse of the encryption function for both the ciphers. Then going ahead and discussing keys for both the stream and block ciphers, the same for the block cipher, the same input key will and the same input block will give the same output block, as well as for the stream cipher as well. The same key produces the same key stream. So we should not be using this repeated. We should not repeat the key, and to actually fulfill that easily, we can use something called an initialization vector, which when combined with a secret key gives a unique session key, which creates multiple different keys for us to use. In terms of key weaknesses, there are multiple key weaknesses that we have to make sure for both the ciphers, such as the key and output should not be correlated. There should not be the keys, multiple keys that are used that should not be related, etc. Then we move on to noticeable block ciphers. So DES is a very old block cipher, which operates on a 64-bit blocks, uses 56-bit keys. It's a facial network, but as we know, it's a small key size now, so it can be brute force easily. 3DS was actually was actually developed on the basis of DES, which actually uses DES 3 times. The key size here is larger, which is 168-bit, but it is essentially 112 bits. But then since it uses DES 3 times, it's literally significantly slower software performance than DES, almost as 3 times, and it's again ineffective against brute force attacks. So there's a better newer algorithm that was used now, that is Advanced Encryption Standard, AES, which is a standard encryption for algorithm for US federal organizations. It supports various key length, and it's a very efficient and very strong algorithm. And similarly, two-fish algorithm has variable key size, and it works well on small hardware and software. Then in noticeable stream ciphers, we have the algorithm RC4. It's very efficient for real-time processing, but over the time it has been vulnerable to many attacks. Then there is algorithms like A5, HC128 or HC256. HC128 and 256 are part of portfolio of the eStream project. They support 128-bit keys and 256-bit keys. They are very secure and they run very efficiently on modern processors. To see their commercial utilization today, in block ciphers, DS, double DS are no longer in use, but triple DS is still seen somewhere in the electronic payment industry. AES is widely used and for high performance computing, and two-fish algorithm is somewhere used in smart cards and embedded hardware. In terms of stream ciphers, RC4 is no longer used because of vulnerabilities. A5 is still used somewhere in the GS and cellular industry, and HC128 and 256 are used for bulk encryption and software. When we come to the hardware application for the block cipher, so here we are discussing in an experiment by Dinuri and others, where they actually compared 19 different lightweight block ciphers and using 3 metrics of interest, such as execution time, memory, binary code, etc. And they kind of used 3 different microcontroller. They used this on 3 different microcontroller platforms. And according to their results, the lightweight algorithms Chasqui and SPEC perform better for the specific IoT security. In terms of stream cipher applications on hardware, this is an experiment by M.D. Galanis and others, and as stream ciphers are useful for wireless communication protocols, so they used 5 different stream ciphers and again compared their performances in terms of throughput and related metrics. And what they found out was that Helix stream cipher had the highest throughput and even the smallest key setup time. It was the fastest among all the 5 algorithms, and it was essentially tested on FPGA. Next, we move on to the case study. In this case study, we basically AES and RC4, the block cipher and the stream cipher, were implemented on a single computer, and we just compared different metrics of the computer, the hardware metrics. So in terms of encryption and decryption time, the RC4 took less time with respect to AES to encrypt and decrypt, and we infer that due to the single unit of RC4, it could take less time, and the large unit block of AES, the data chunk, it takes higher time for AES to encrypt. Then for even as shown in the graph and shown on the slide, in terms of throughput, RC4 is overall fast in nature and it consumed lesser power than AES. Then again, we could conclude from that because of the small data chunk size of AES, RC4, it could take lesser time. It could give higher throughput. Then in terms of memory utilization, AES consumed more memory for larger files as shown in the graph, and again for the same reason. But for the CPU time, RC4 needed more CPU time to encrypt smaller size files, while AES needed more CPU time to encrypt larger size files. So in this case study, we saw that overall in terms of the hardware implementation on a single computer, RC4 performed better, but we can't really compare it on a larger scale that way. So to conclude, we found out that stream ciphers are derived from block ciphers and both differ in terms of their operations and their applications. But the thing is, even with their sometimes stream ciphers are fast, or even with their different kind of metrics that we found in different places, they are still both widely in use today, and they are not replaceable by each other. They serve their own purpose, they have their own applications and their specialities. And we found out that for each vulnerable cipher, every time there was vulnerable cipher for both block and stream ciphers, cryptographers developed better ones along the same principles, and we still have very strong both block and stream ciphers. And that's it for today. Thank you.